it doesn't have speaker notes. You can keep it like that.
Cool.
It's big enough.
Shall we get started? All right. So my name is Jordan Dimov, and I work at what I work? OVP. Right. OVP Commerce. we, we've been we've mostly been working with Python on a core components for technology that powers products and offers and pricing and all of that. So we've been working on this for 6 years using Python, and it's become kind of a big-ish piece of software. And so I think we've run into various limitations that you can imagine, both with the language and with our design of the thing. And we've been rewriting various pieces of it and at multiple times the whole thing. And during that process, we've learned a thing or two about, what are good ways to design larger software like that. And one thing that I personally have come to extract out of this and, learning from other languages and what other people do and other approaches to designing large-scale software is that functional programming may be a thing that has some benefits that, could make it actually easier for us to manage this big thing, so we can focus on having it do what it's supposed to do reliably and without the complexity of it, growing more than it needs to be. So it is already a complex system in terms of the requirements, in terms of what it needs to do. And we don't want to make it any more complex than it needs to be. And to some extent, that's unavoidable. In the process of designing large systems, you introduce some additional complexity there. But the point is to keep that unnecessary complexity to a minimum. And I believe that functional programming has a thing or two to teach us about this. And being a Python developer myself, I've looked into, is Python good enough to support these functional primitives that can give us these benefits? And the answer for the most part is yes. It's not a first-class functional programming language. When you think of a functional language, you don't typically think Python. There's things like, Lisp and Scheme and Haskell and Erlang and Clojure and all kinds of things that are designed primarily around the idea of functional programming. And Python is not one of these languages, but it does turn out that it sort of has enough to give us the tools that we need to apply some of these concepts and get some of these benefits. So, quick little joke to start with. What do you call a snake that is 3.14 meters long? You call it a python. Very clever. Right. Let's get to the point. Okay. All right, Python. So, what is functional programming about? As the name suggests, it's about functions, right? And so functions, what are functions? Are these small, self-contained components that, pieces of code that are supposed to transform data, okay? They take some input, they do something with it, they produce an output. Why small and self-contained? Because it's easier to manage them that way. The smaller they are, the easier it is to understand what they do, to design them well, to test them, to maintain them, and to combine them together. So Python obviously gives us functions. There's two ways to define functions in Python. You can use def to define named functions and give them a name, so you can call them by the name. Or you can use anonymous functions without a name using the lambda construct. You just define the arguments, define the body of the function, and just pass the whole lambda object to whatever needs that function. Also in Python, functions are first-class citizens, so they can also be data, meaning that they can be passed to other functions as arguments, and other functions can return functions, as the result of that computation. So in this way, we can do higher order stuff. So we can have functions that work with functions, so it gives us more power. Now, Python is fundamentally an object-oriented language, right? So just about everything in Python is an object. Functions themselves also are objects in Python. So this is what, this is the underlying mechanism that allows us to actually take functions and pass them around and treat them just like any other object, really. They have attributes, they have properties that you can look into, you can inspect, you can pass them around just like any other object. Now, if you wanted to build something more complex than a simple function, then the idea in functional programming is to combine these functions together. And there are different ways you can think of how you can combine these functions, but the most widely used, widely accepted way of combining functions in functional programming is through composition. And composition is the idea of taking one function which has some inputs, it produces an output, passing this output to another function that takes that, does some additional transformation, then maybe pass it to another function, and so on until you get to the point where you have your result. Now, if you are familiar to some extent with the Unix philosophy, you can see the correlation there. So the Unix command line sort of has this same, it doesn't usually talk about functions and composition, but the idea is the same. You have these small command line utilities that are self-contained. You are encouraged to write Unix programs so that they're small, that they do one thing and do it well. And then you are encouraged to combine them via piping normally, which is, piping, you can think of it as the shell idea of function composition, right? And so in the shell, you pass the output of one function as the input of another, and this is similar to composition in functional programming. And so this gives us, small components that are reliable, flexible. It's easy to combine them together in ways that maybe you didn't even imagine initially when you were building that function. Other people can take your small functions or your small Unix programs and combine them in ways that you didn't even foresee. But this is possible because they're small and interoperable and flexible. So it's like Lego blocks. You have a small set of standard blocks that you can combine together and make all kinds of things. But you might be asking, what's the big deal with this? In Python with object-oriented programming, you kind of have the similar idea, right? So you have objects which also are designed to encapsulate small or manageable pieces of data and functionality, and then you can also compose objects in different ways and have them interact with each other. So how is functional different? How is it better? Why is it worth thinking about? So let's have a look. So this is a very simple, very basic, Python object. And what is an object in Python, or in any object-oriented language? Really, the idea of an object is you have some data, which represents the state of this object, and you have some methods that manipulate this data, manipulate the state of that object, and allow other objects to interface with ours and to talk to it, to do things together. So if we have a simple bank account object, which has a property balance and some initial value, and we have an update balance method, which takes a transaction value and updates the balance of this bank account by adding this transaction value to the current balance. Okay, this transaction value can be positive or negative, doesn't matter. The point is, this method defines a single operation, sort of small and well-defined, that we want to do to the balance to affect the balance. And so if you were to use this, you would say, let's create a new bank account object by instantiating this class, and let's update the balance with a certain amount, transaction, and we want to print the balance. Now, what do you expect to see? In this case, when we start with a balance of 0 by default, we add 5. When we print the balance, we expect to see 5, right? We've added 5 to 0. And most of the time, this is the case. And this is what you expect, and you'll be a bit surprised if you didn't get this. The thing is, it's entirely possible, and in larger systems, in fact, it's more than possible. It's actually likely that you may not get the result that you expect out of this. How is this possible? Well, in larger systems, when you're passing this object to other objects and other code that works with it, in Python, it's possible for other objects to modify the internal state of this one. You don't have the concept that you have in Java of private data. So you have some convention, but it's entirely possible for other objects to modify the state of your object. And in larger systems, it's not always obvious what these other objects are, what these interactions are. When you have 20 or 30 of these things interacting with each other in say 5 different ways each, you can imagine how this complexity grows exponentially. And to the point where it's really not possible to keep all of this in your head. So you can help yourself with UML diagrams and things that sort of show the interactions of things, how these objects affect those ones. But even with that, even with these visualizations in a large system, it's very difficult to get a full grasp of the system and how the state of things is affected by other things. More than that, in a less subtle way, if you actually wanted to run multiple threads or multiple processes or code and concurrent code, then it's possible that you can pass it, in one of the methods of this object. You can start another process that actually also has access to this and can modify the state of this object. And so in concurrency, it gets even more complicated. It gets even more difficult to keep track of the internal state of things. So this is what's known as imperative style of programming. You have statements that go one after the other, and you sort of tell the computer what to do. You're saying, take this, do that, take the balance, increase it by the transaction value. You execute statements one after another. In object-oriented programming, we try to break the state that we work with into smaller, manageable pieces, and we take care to implement controlled mutations, right? So the methods that we expose are supposed to sort of control the ways in which state can change, from one state to another. And we encapsulate this state into objects and the behavior, and we try to sort of hide the internal state by exposing an interface to other objects. In reality, in large systems, as we said, we often end up with objects modifying the state of other objects. Let's contrast this with what we have in functional programming. So this is again a Python example of a more functional style of programming, which in effect is supposed to achieve the same bank account updating functionality. So instead of an object, we use a tuple. And as you know, tuples are immutable in Python. You can't really change the internal state of a tuple. You can take a tuple, you can do things with it. You can produce another tuple, but you're never really changing the internal state of the tuple, okay? And this is kind of a big idea in functional programming. If you tend to work with immutable data. In Python, you have some immutable types of data and others that are mutable. So if you wanted to work closer to functional programming, you'll stick to immutable data. So let's see what's happening. We have a named tuple just so we can give the elements names instead of remembering what the position of each element means. So we have a named tuple bank account with a balance. And we have an updated balance function. The function takes an account, takes the transaction value, and returns a new bank account tuple, the balance of which is the current balance of the account that we passed in, plus the transaction value. And the way we would do this is we would say account initializing a tuple with state 0, and then we would print the updated balance of the account, adding a transaction of 5 to it. So what do we get? We get a new bank account with the correct updated balance. The initial account object is still there. It didn't change. So this is what we mean when we talk about transforming data in functional programming and working with immutable data. take an object, you take some data, you do some transformation with it, and you produce new data. This is known as declarative style programming, in which we sort of tell the computer what we want to get. Okay, we don't necessarily tell it do this, do that as a sequence of statements. We say we want to get the updated balance. Okay, and we call this function, and it does whatever it does, and it gives us the updated balance. So we're working more with evaluating expressions. In functional programming, so we said that in object-oriented programming, we sort of try to manage complexity by encapsulating state and having well-defined interface that sort of controls the mutations of that state in things that we think we can understand and others can understand. Now, in functional programming, we manage complexity by avoiding the mutation of state altogether. Okay. And so we're focusing on getting what we want out of it, getting things done instead of actually having to worry about all the complexity around maintaining state. And we may get back to these examples later, but let's carry on with some ideas from functional programming. One of the ideas closely related to functions is about purity. So some functional programming languages are known as pure languages. Not all of them are. In fact, most of them are not. But what is purity? It's about functions that, as we said, they take some data, they do some transformations, they give you some new data, but they don't have any side effects. Okay, they don't affect anything else. They don't affect any other state. They don't change global variables. They don't access global variables. They don't read additional data from the environment. They don't generate random data. They don't read data from random number generators that are external to. So anything that is not passed in as arguments to this function is not taken into account. And when the function returns, you get your result without the function affecting anything outside of it. Now, when you stick to this, when your functions are pure in this sense, you have a guarantee that when you call a function with certain values as arguments, you will always get the same values as output. Okay, because there's no external there's no external information that can affect the transformations that you do to this data. So again, if we were to call our updated balance function with our account and a transaction of 5, you would always get 5, assuming started with 0, and there's nothing else that can affect it. No other objects, no other functions. You're guaranteed to always get the same results. Because of this, you get numerous benefits. So it's easier to follow and understand the code. It's easier to prove correctness because you always get the same results from the same initial data. You can actually use some cool mathematical tricks to have rigorous mathematical proofs of the correctness of your software, really. Because you can start with the individual small functions. You can prove that when they get data A, they always transform it to data B. And when you compose functions together, you can also infer with the same mathematical rigor. You can infer statements and the correctness of your entire software system, which is a composition of individual small functions. This also makes it easier to test, to unit test individual functions and to test larger structures, because there is no external state that your function uses or external state that your function modifies. There's no need for patching and having complex mocks and things that simulate the environment, because there just isn't any of that. So your unit tests really are, here's this input, this is the output that I expect. Run the function, does it give me what I want? That's what it is. And it's also, as I mentioned earlier, it's also much easier to safely implement concurrent software. Okay, so threads and processes that run in parallel, because you're safe in the knowledge that other processes, other threads will not affect the state of your current thread. In stateful systems, this is normally managed by using locks. You have some data with state, and then you have these other processes that also may want to access this data. And so to to sort of ensure the safety and the consistency of that, there's different approaches, but normally you put locks on it. You'll say, okay, this process is now writing to this data, nobody touch it. And then, okay, this lock is released, other process can now access this data. And there's no need for any of this when each of your process uses only these kind of pure functions that are not affected by anything and do not affect anything else. So let's get back to the software that we built in the real world, because everything that we said so far, it sounds really good. Uh, but it sounds a bit like an ideal world, doesn't it? Like, are you really able to achieve this, these small components, this purity in the real world, in a complex software system that you're building? And we'll see if we can get to the answer to that, but let's first talk about, let's make a distinction between two kinds of complexity that we encounter when we build complex systems or big systems. So there's what we call the essential complexity. Okay, this is, you're building a system because it has some requirements. You have a user or a group of users who want to get something out of it. They want some defined interactions with this system. They want to be able to do things with it reliably. And so once they formulate the problem and everything that this system needs to be able to handle, this kind of gives you the essential complexity. Okay, these are things that your software is going to have to address no matter what. It's sort of complexity that you can't run away from. It's things that you have to deal with because they're inherent to the problem that you're trying to solve. It's essential to users' requirements, and will need to be dealt with regardless of your choice of programming style, regardless of languages, technology, whether you're doing co-op or functional. And then as you start building more and more complex systems, you also, unavoidably, you also introduce some additional complexity that was not really inherent in the problem, okay? These are things that were not forced onto you by the user, but are things that sometimes are forced onto you by the technology that you have to work with, or the choices that you've made in terms of methodology and languages and different data structures and all of that. So accidental complexity is not essential to the problem. It's introduced by the specific choices of technology and programming style and design patterns that you choose. When your code adds to its own complexity beyond what the problem requires, that's how accidental complexity is added to your system. And in the ideal world, you should not really have any of that. But in the real world, it's unavoidable. And, it, there's things, again, there are things that you just can't run away from. There's things that your environment enforces you to sort of add this complexity. Then there's other things that maybe are not unavoidable, but you end up doing them anyway. It's usually not you, it's usually your colleagues that add this accidental complexity. But sometimes it's you too. It's just choices that we make. Sometimes we're under pressure to deliver something and we say, I know this is not the ideal solution, but I'm going to do it anyway, and maybe I'll deal with it later, or maybe I'll forget to deal with it later. And that's how this accidental complexity adds up. Now, the thing about it is, it's not just that it sort of increases the complexity of the system as you add it, it also tends to compound. It tends to attract other complexity to it, because then you need other code to sort of help manage what you just did the wrong way. And there's lots and lots of examples of this, smaller and larger. The point is, there has been people, academics, and practitioners sort of thinking about these problems, and they tend to come to the conclusion that managing state, what we just saw with especially the object-oriented approach to managing state, is kind of, let's not call it the root of all evil, but it is the main source of accidental complexity in building software. Okay. Because most of the time, these things that you end up doing that are not ideal really have to do with changing the internal state of things and managing that and maintaining it in ways that maybe are not really essential or necessary to the problem. So most compound data structures, other than simple things like integers and strings and other, like arrays, dictionaries, in most programming languages, including in Python, are mutable. Okay, so in Python you have lists, you have dictionaries, and these things are mutable. They're things that you can change. You can take a list, you can change the fifth element of it, and that's the same list, okay? You don't get a new list, you have the same list, and other parts of your software see the same list with the updated fifth element, and maybe it's not always the case that they expected this fifth element to be updated. So in the olden days, in the 80s and 90s, I don't know if you've done any programming with languages like BASIC or even assembly with jumps and things like that. But there used to be this go-to statement, which again, we're talking about declarative languages, procedural, where you have statements one after another, and you have these each line numbered, and you have line number 10, do something, line number 20, do something else, line number 30. If the accumulator has this state, then jump to line 50. And you go to line 50, and then your code continues there. Now, the problem with that is at line 50, you're not sure how you got there. Did the control flow come from the previous line, or did it come from somewhere else, sort of jumping using this go-to statement? And that introduces accidental complexity, okay? And so there was a famous paper saying the go-to statement is considered harmful because you don't know how you got to that point where it sent you. Similarly, with this mutable state, with these data structures that you can change outside of the defined interfaces, you end up with accidental complexity because some parts of your code don't know how other parts of the code got this state to what it is. Or even some of your colleagues don't know what you had in mind when you created certain objects that change state in a specific way, which is not always obvious. I'm gonna be pointing to you from now on when I say colleagues. Right. Okay, let's carry on with functional. So in functional, there's this idea of two types of evaluation. There's strict and not strict evaluation. With strict evaluation, you have your function that takes some inputs and it's evaluated and you get the result right away. With non-strict or lazy evaluation, which is more commonly called in Python, you get your function, it takes the data, but when you evaluate it, when you call the function, it doesn't actually run the code, it doesn't transform the data right away. Instead, it gives you an iterable, it gives you an object in Python, which is ready to give you the next state, but it only does that when it's needed, when you actually ask for the state. So the point of that is, with iterators, I don't know if you use iterators or generators in Python, things like that, but the point is, if you have, imagine, for example, you have a large amount of data, okay? Or you're reading several gigabytes file from disk, typically, as a common simple example. And you don't want to read all of that memory, all of that data in memory, or you cannot because it's too much. Or maybe it's a stream and it's potentially infinite, so you can't read all of it. And so that's why you have iterators that you define the operations to be done on each piece of data as you read it in, but then you get this iterable object that you can then pass it to other iterable objects that then apply another transformation, and you can chain them like this as much as you want. And then at the point where you actually want to get the final result, you say, okay, go ahead and evaluate the next state. And each of these iterators evaluates, gets some actual piece of data, gives you the final result, and you can keep calling it, consuming more and more data. So iterators evaluate only when it's necessary. They allow work to be performed on large amounts or streams of data without keeping it in memory. Iterators are typically immutable. You're not normally supposed to change the internal state of iterators because then they get really confused. So you can treat them as immutable for most purposes. And they are composable, as the example I just gave. Okay? You can piece them together. So they're really good, among other things, they're really good for one specific kind of transformation known as reduction in functional programming. So things where you have a sequence of data or large amounts of data, and you want to get some aggregate value out of that, like you have a long list of numbers, you want to get the total, you want to count the list of words in a book, you want to find the average in a list of prices or things like that. So that leads us to sort of the third kind of construct that you have in programming languages. So you have data, you have functions that work with data, and then you have in imperative and declarative languages especially, you have control flow. Okay, you have things that decide what's going to happen next. You have loops, you have conditionals, if statements that sort of branch your code and increase complexity. Okay, every time you branch your code, you sort of have at least two different parts to think about, to keep in mind. So so you increase the accidental complexity using control flow structures. So with data structures, we use data structures to manipulate many similar pieces of data as one entity. Okay, so we have compound structures that we can treat as one thing. With functions, we can use composition to put multiple functions together and again treat it as one entity. And both of these things help us manage the essential complexity of the problem. But what do we do with control flow, which seems to be mostly around accidental complexity? How do we manage that? Can we take sort of several control flow structures and compose them together, or talk about them as one thing? It doesn't come naturally, okay? It's not something that we typically do. But it turns out that this is one area where functional programming really shines. And not in any profound way, but in a rather basic way. So in functional programming, we have these patterns of control flow. And if you look at this slide as sort of a map from the left column to the right column, in imperative languages, you have loops that modify data. Okay, so you take a list of data, you go over each element, and you do something to that element to get it to another state. In functional programming, you have a function called map, which is a higher order function. It takes two things. It takes another function which defines the transformation that you want to do to each element in your sequence, and it takes the sequence and it applies your function to each element, and it gives you a new sequence with your function applied, with the transformed data. So this is one simple and easy to understand and obvious way in which you have a function that does what we started with. That is small, simple, does one thing and does it well. It's a higher order function, but it transforms data. It takes your data, it applies some transformation to each element, gives you new data. Similarly, what else would you typically do with loops? You might have a loop and that goes over a sequence of data, and you might have a conditional inside of it that says, if this next element matches my condition, let's keep it simple. Let's say you have a sequence of integer and you want to only extract the even ones. So you have a loop, you have an if statement that says, if the number that I'm looking at is even, then I want to keep it. If it's not, I want to go on to the next one. And you can imagine these 4 or 5 lines of code that do this. Now in functional programming, you have another function called filter, which does the exact same thing without these imperative control flow structures. And in structure, it's very similar to map. Again, it's a higher order function. It takes a function that defines your condition, your criteria for keeping things. And it also takes a sequence. It applies the function called the predicate to each of the elements. And if the predicate is true, it takes that and carries and gives you a new sequence that only has the elements that you want. What else do you typically do? You have a loop, and you go over each element of the loop, of the sequence, and you sort of add things together, or you update some state. You keep a sum, or you keep an average, or you keep a counter. That's a typical construct. And again, in functional programming, you have something called reduce, or a related operator called fold. Function, not operator. And again, what they do is they take a function. Now, this function is supposed to be able to do something with 2 consecutive items from the sequence. And they take a sequence. And they start looking at the elements, the first 2 elements. They apply your function that sort of that knows how to aggregate these 2. And then take the new value, the return value of that function, and the next element, again apply the function, get the result, take the next element, apply the function, get the result. And this is how this potentially infinite sequence or a large sequence of items is reduced to one aggregate value. Finally, well, my final example, I mean, there's lots of these that we can keep going, but my final example is you have a loop, and this is one that personally has been irritating me often in code, and I've always end up thinking, you know, there should be a more natural way to do this. But this is what it is, okay? So you have a loop that goes over a sequence of things, and you have a condition that says, you know, if the thing that I'm looking at is of this type, I want it in set A. And if it's of the other type, I want it in set B, okay? I sort of want to dispatch into 2 or 3 or more different piles. I want to categorize things. I want to classify them, okay? And typically, in imperative programming, you would go over each sequence. You would have your if statement that or condition that says, you know, checks the type of thing, decides which container to throw it in. And in functional programming, we have something called group by. And in Python, you don't actually have this in any standard library, but there's a very cool, I'll get to that. There's a very cool external package called tools with a Z at the end, which gives you a collection of things like this that are rather common actually and interesting and good to know about. But group by, this is what it does. Again, it takes a function that sort of determines the type of thing or which does the classification for you, and then it takes a sequence and it returns, in this case, with this implementation, it actually returns a dictionary where the keys are the different categories that you want, and the values are lists of all the things that belong to each of those categories. 5 minutes. Let's sprint through the rest. Sorry. Right, so the point of all this is these functional programming higher order functions, they give us names that we can use to talk about these control flow patterns, okay? This is not very dissimilar from the other patterns that you may know about if you've done some Java or if you've read the Gang of 4 book about, you know, software design patterns. But these are also patterns of common tasks that you do that we can now give names to. So the big idea here is that naming control flow patterns helps us manage accidental complexity, okay? With data, we have data structures. With functions, we have composition. With control flow, we can use these higher order functions, sort of name control flow structures, and be able to work with them easily and also combine them. Now, because these things are functions, you can compose them and you can do more complex things with them. So this is an example of the group by that I showed. Okay, on the left side is the typical imperative programming way of doing that with the loop. On the right side, all of that really is replaced by one function call, with is even being your classifier. And so this control structure is now explicit, okay? We've given it a name. And as design of Python says, explicit is better than implicit. And so if you want to carry further, what you can do is you can go to the Python documentation, search on the internet, you can get some books. But my point is it helps, it pays dividends to sort of grow your vocabulary of these control flow structures, of these patterns that functional programming gives you names for. And knowing when to apply them, knowing when to use them really helps simplify your code and manage complexity better. Yep. So let's wrap it up then. Just one final idea. Functional programming does have some limitations. With all the benefits that it gives us, it's actually a bit more challenging to debug in the way that we're used to with imperative programming. It's easier to peek into state because you don't have state typically, or not in the way that you're used to. It gives you less fine-grained control over the flow of execution. So you can't actually break in the middle of a function and go do something else like you might do in a loop. And so because of that, it's actually a bit more difficult to optimize things for performance, right? So with imperative programming, you can have your loop, do your things, and decide at one point that, okay, it's not, it would save me time if I didn't do the rest of this work, and you can break or continue, do things like that. With functional programming, it's trickier to do these things. Now, the good part is when you use Python, Python sort of gives you enough functional primitives so you can take advantage of these cool functional things that we talk about, but it also obviously has the typical imperative constructs that you can use to optimize for performance, to do your debugging the way you're used to. And so I encourage you to sort of use both of these and exercise judgment. Try to do, because this is less natural to us as Python developers, try to think more about these functional ideas and apply them where you think you may benefit from them. But when there is need for fine-grained control, then go back to your old ways. Why do functional programmers tend towards anarchy? It's because they've learned to hate state. Right. I have some books. None of these are actually Python books. Like unfortunately, I can't recommend a good Python book on functional programming. I think there are at least two I know of. There may be more. And there are some good resources on the internet. And these books, they're good. You can learn things from them, but I don't think they actually do the two that I've looked at, I don't think they actually do a good job of giving you the fundamentals and helping you understand why all these things that they talk about are good for you. But I think you now have this understanding to some extent. So hopefully you'll be able to take advantage of these books. Thank you. I'll give it to you and you make sure you post it. Oh yeah, right, you have it. So yeah, if you can you just post the PDF to the channel to Slack? On community page, that's all. Mm. Yeah. So what I found is if you want to learn about functional programming, don't look for Python books. There are other books that are very good at giving you the fundamentals, the understanding, and then take the Python books and see what the Python tools are for these things, but once you have the fundamentals. And these are some books that can help you. There are a lot of others that are good. So SICP is Science and Interpretation of Computer Programs. It's an MIT book from a long time ago. So it's a textbook that they use in MIT to teach programming, actually. They use it as first programming book. And it's not specifically about functional programming, but it does have a lot of the fundamentals that you need for this, and has a lot of good exercises. Now, the language that they use here is a kind of Lisp called Scheme, but you don't really need to get into that. Elixir is one of my new favorite languages. I don't know if you've heard of, you probably know about Erlang. Now, Elixir is sort of Erlang with a syntax that is closer to Python than to Erlang, because the thing that people don't like about Erlang is the syntax. It's very different to what you're used to, but it does have other great things that it gives you as a virtual machine. And so Elixir is a language which sort of brings your syntax that, if you're familiar with Python, it's easier to get used to, but it is a functional programming language. And this book, there are a few books about Elixir, but this one specifically talks about the concepts that I've talked about related to functional programming. This is a Python book, Python programming. Again, it's quite comprehensive. It covers a lot of things, but not so good on the fundamentals. The tools package that I mentioned, have a look at the package and the documentation. Documentation is great. And there's this paper. If you Google it, you'll find a PDF out of the carpet. this is a very well written paper that talks about these concepts that I mentioned about accidental versus essential complexity and managing state and all of that. Thank you.